My talk is about it, not so much about the science, but rather the a tool for lunar impact science, looking for volatiles, obviously. And this is a result of a case study we did for disposing one of our ESA satellites. And I will come to the details in a minute. So next. Oh, I'm sorry. My collaborators are Neil Bowles and Brendan Hermelin and Norbert Zirkov of the University of Hawaii. Next slide, please. Right. So overview. After a short introduction, I will talk about what we try to achieve with impact experiments in terms of understanding lunar volatiles, and then I will present the case for the disposal of the Herschel telescope. And after that, there will be a short discussion on what kind of target site we had in mind when we were discussing this case. And finally, we'll have a conclusion. Next slide, please. All right. Obviously, like we heard in the earlier talks by Larry, for example, that there is some things we still don't understand very well about the geochemistry and in particular the volatile contents of objects in the solar system that don't have any air. Airless celestial bodies are still to some extent mystery to us. And there are very famous missions like Deep Impact and LCROSS, obviously, that have shown that there's high value in impact experiments because it provides real ground truth data, which still needs interpretation, but that is some direct information that we can obtain from those objects. What I would like to present here is a case study that was carried out the end of last year to look at a potential lunar impact disposal for the Herschel Space Telescope, which is quite a massive object, one of the most massive objects that's controlled by humans in space. Since then, unfortunately, the decision was to dispose this telescope into interplanetary space, so this opportunity is lost. But I would like to present anyway what kind of ideas we had. And a good thing about this is that we are able to target such a mission towards almost vertical impact like LCROSS was. This is quite different from another class of impact or impact disposal, which is like Lunar Prospector, Smart 1 or GRAIL, which are more obviously moon orbiting missions. And they would impact more in a more oblique way, and that has a very different physics behind it. So in the next slide, I will talk about a couple of things, what we try to achieve with those impact events. So next slide, please. Right, on the right-hand side, I have a picture from the Diviner results, which should show the believed or the modeled permafrost depth on the poles of the moon, just to symbolize the potential that is there. And this is a little bit the rundown of what we try to achieve with this. Obviously, volatiles and in particular water are interesting for exploration, and the impact experiments they do, besides delivering data, they also give us information about how to release those volatiles from the ground on the moon, and that already tells you something how to extract that for exploration missions. And ESA obviously is very interested in that. Other aspects have already been named, like we'll have new science in terms of understanding, for example, the difference of the permanently shadowed regions and the low neutron flux regions, how they are associated, and those questions that are still there. And again, this would give us some ground truth on the presence of hydrogen-bearing components on the lunar surface. And of course, more impact results will help us to confirm the LCROSS results to even make them more important. So next slide, please. This is this one part of the study that we did, which was to understand the part of the impact plume that we would be able to see. And there are two very important, for a vertical impact, there are two very important geometric factors. One is obviously the sun illumination of the plume, and the other is the Earth direction. So how far can we look into the crater from the Earth? So those considerations are very important for ground-based observations, because normally for a disposal mission you don't have a dedicated spacecraft that can be used for the observations. So that's the geometry. We looked at different craters, and I will come back when we discuss the impact site selection. Now for the case of Herschel in the next slide. Oh, I'm sorry. This is still part of the impact dynamic studies, which shows the escape velocity of the ejecta as a function of distance from ground zero, or from basically from the impact point. And there are different laboratory analyses as well as modeling, and you can obviously see that you get a full spectrum of ejecta velocities, and they are separated through the impact, the position relative to the impact site, and that helps you to understand the ejecta plume. Now, next slide, we'll discuss the case of Herschel. So Herschel ran out of coolant, basically. Was initially predicted end of April 2013. It turned out to be mid-May in the end. And of course, ESA has a very strong policy to safely dispose all spacecraft that we have. And we had a number of options, 4 of which are non-return interplanetary. That's the one that was chosen. Controlled re-entry to the Earth atmosphere. Demonstration mission around the Earth-Moon libration point, followed by the Moon impact. It would have been my preferred, obviously, because we can learn something more from operating spacecraft at the Earth-Moon libration point. That was also not chosen, and the direct Moon impact was another one that would have ended with a Moon impact. I have to add that only disposal options that end with an entry or with a Moon impact are really final. We know from the Apollo 12 upper stage that objects that are disposed into interplanetary space, they have a tendency to come back for dynamical reasons. Next slide, please. So Herschel was originally on an orbit around the Sun-Earth libration point, and those orbits are unstable, but they tend to be connected to the near-Earth environment and to the lunar orbit through what's called the unstable manifold. So you can fall away from those orbits without any maneuver, with a very small maneuver anyway, and then it takes you back to the near-Earth environment. Geometrically speaking, and it's shown here in the graph on the lower right, there are 2 points where those manifolds intersect the lunar orbit, and it's at different phase angles. That means we have 2 kind of general directions where we can approach the Moon from. And unfortunately for Herschel, because we could not really choose the time of departure, we had to depart basically when the coolant ran out. We had to adjust that a little bit, and that cost some delta V to get there. Also we had to allocate some propellant to do correction maneuvers because we wanted to target a certain region on the lunar surface, and that costs also some propellant. Next slide, please. This shows on the right-hand slide the amount of propellant, or delta V in that case, that you need to reach the Moon as a function of departure date. And you can see that there are natural connections to the lunar surface, basically from the north and the south. In the lower right, you see the latitude of the natural injection trajectory. So the first one is the northern kind of, and the second opportunity is more to the from the south. And you can see that the dates are in June for a north approach, and end of July, beginning of August this year for a south approach. And so those were the options at the time that we studied. So if you go to the next slide, please. This is the trajectory that was chosen in the end. We would depart the Sun-Earth libration point orbit and have a couple of trajectory correction maneuvers, and then directly impact the Moon on July 29th, basically at the South Pole with a velocity of 2.4 kilometers per second and an elevation or approach angle of around 70 degrees. Next slide. Of course, if you approach the Moon, you want to certainly hit a certain area, the impact area that you selected. For that, you need to do quite a bit of navigation. And we studied that, how well you can determine the area, and that depends on the several factors: the tracking accuracy, the noise created by the spacecraft, noise meaning dynamical noise due to the actuation of the thrusters that occur on board in a closed loop manner. And all those things were put together to find out that we can actually reach a targeting ellipse in the order of 10 kilometers in size. Right, next slide, please.
Okay, Marcus, you have 4 minutes until the end, which is 2 minutes until questions.
Thank you. This shows one of our target area, which is, if you know the coordinates by heart, it should be Cabeos A, the original target site for L-Cross. We chose that because we wanted to understand a little bit better the environment of the Cabeos crater region. At the end, there was not a lot of time to discuss about different impact sites, because we started end of last year. We had to prepare that for mid this year. And this was basically based on the temperature. So we wanted rather low temperatures at the impact site in order to be have a good likelihood of finding something, despite the fact that obviously from a scientific point of view, we want to understand if there's water that can be generated by impact, even though the region is not very cold. If that would be even more interesting. But the colleagues involved, they were more, for them it was more important to actually detect some water at a new site, distinct from the L-Cross site. All right, and now we go to the next slide, which is already my conclusions. So I've presented this case study for deposing Herschel at the lunar South Pole for scientific purposes. The selection of the impact site has been done so we can exercise our current understanding to a maximum effect. So there was a compromise to have it sufficiently similar to what we know about L-Cross, but still different. So that was the basic idea behind it. We would have had a very good visibility from the ground of the Cabeos A impact on July 29th this year, and we would have had a mission in the end with only 100 meters per second needed for the departure, and there was another 29 meters per second for the navigation delta V needed, and that was actually available on Herschel. So that is sometimes a limiting factor, how much maneuvering capability you have, and that was quite good for Herschel. So and we found that we can be within 35 kilometers, 3 sigma. This can be much improved if you are more ambitious with the targeting. So, for example, instead of doing the last maneuver 3 days before the impact, you do it only 1 day, and then you're already below 10 kilometers and 3 sigma. So current and future missions I propose to actually think about lunar impact disposal, because we can learn something on lunar volatiles from it, and on top it is a final disposal mechanism. Candidate missions that I have in mind are Planck, Gaia, James Webb, Huafu 1, and Solar C. Thank you.
All right, thank you.
Should I go ahead with questions?
Yes.
Okay, there are a couple of questions. One from Rick Elfrich. He would like to know when Planck could be targeted.
Unfortunately, they are already not considering lunar impact anymore for Planck. So the end of mission is October, November this year. And because there's no guideline within ESA right now, people are quite afraid to think about lunar impact, because it could be considered contaminating the moon. Those issues are important there from a programmatic point of view.
Also, from Catherine Niche, do we have time for one more question? She'd like to know if you could comment a little on why was the decision ultimately made to dispose of the Herschel in interplanetary space?
One reason I already gave, which is the fear of being viewed as an agency that contaminates the moon. The other was programmatic decisions in the times of austerity, where we had to shorten other extended missions. Was said that we cannot extend Herschel by three months while we're shortening others.
I realize we're already over time. Should we proceed on?
Yes, I think so.